610, integrating with long division and completing the square. When we are trying to integrate a rational expression and we have something we don't recognize, or we have the degree of the numerator greater than the degree, greater than or equal to the degree of the denominator, as you can see here, division is quite helpful. Also, we will be completing the square to arrive at antiderivatives that are very familiar to us. So these techniques are very helpful and allow us to integrate more difficult functions. So let's just go ahead and begin. Maybe a little reminder on how to use long division, and then we'll talk about synthetic and if synthetic division can be performed. So just first taking a look at this, you might say, well, why can't I use u substitution? Well, if you let u be that numerator 3x cubed minus x squared your du is going to be 27x squared minus 2x, and you'll never get that. You'll never be able to find a way. Plus, we don't have something where the function is in the numerator and the derivative is in the denominator. So rational expressions, the first thing you want to do is see if the derivative of the denominator is sitting in the numerator, so you could possibly have a natural log as the antiderivative, and that's definitely not the case. The next thing you want to look at when you have a rational expression is division. So here we go. We're going to go ahead and divide using long division. So we're going to perform the long division over here, and then we will rewrite our integral. So we're going to have x minus 2, and we're going to divide that's our divisor, into 3x cubed minus x squared minus 5x plus 1. So I usually call this x here the decision maker. In other words, we'll decide what we have to multiply x by to get 3x cubed. And of course it would be 3x squared. Now after you make that decision, now you have to go ahead and multiply x minus 2 by what you wrote up here. Okay, so it's 3x squared times x, which is 3x cubed, minus 6x squared, multiplying it by a negative 2. Now make sure you subtract everything. So I always put parentheses around that when I subtract. 3x cubed minus 3x cubed, we planned it that way. That is 0. If those two terms didn't cancel out, then you made a little bit of a mistake. Okay, negative x squared minus a minus. So negative x squared plus 6x squared leaves a 5x squared. Now we'll go ahead and drop everything else down. Okay, let's go back to our decision using this x. What will we multiply x by to get this 5x squared? And yes, it is a 5x. Once we make our decision, we'll take 5x and multiply it all by x minus 2. So we will have 5x squared minus 10x. Don't forget to subtract and put parentheses around both of those expressions. Now we're going to have 5x squared minus 5x squared. Those cancel or equal to 0. We planned it that way. So now we have a negative 5x minus a minus. So we have a negative 5x plus 10x. That would leave a 5x and bring that 1 down. We can still keep going since we're using x as our decision. So what would we multiply 5x by to get a 5x? You guessed it, just a 5. So now we multiply 5 by x minus 2, and that would be 5x minus 10. Same method, subtract the entire expression. 5x minus 5x leaves nothing. We planned it that way. And 1 minus a minus, 1 plus 10 leaves us with 11. Now, 11 is what we call the remainder. Now, if you remember with division a long time ago, this is actually equal to 11, or the remainder, over the divisor. So this function divided by x minus 2 is equal to this expression, to that polynomial with that remainder term on it. Okay? So I hope you remember that. I'm sure you do. Just take a little practice. So guess what? Now we can rewrite our integral. I'm going to put a little star up there and a star down here. That way we know we're down here and we're rewriting our integral. So this is equal to the integral of 3x squared plus 5x plus 5 plus 11 over x minus 2 dx. And we did that because these are very easy to integrate. So that's equal to x cubed plus 5 halves x squared plus 5x plus, I want you to think about this, the integral of 11 over x minus 2 dx is equal to 11 times 1 over x minus 2 dx. The derivative of the denominator is sitting in the numerator. The derivative of x minus 2 is 1 dx. So we would have this equal to 11 ln, absolute value of x minus 2, plus a constant. So that's what we have here, 11 ln, absolute value of x minus 2, plus a constant. And this is just that one term. So I'm going to go ahead and erase this. Okay? So we want to make sure we understand what we're doing here and why we did it. We wanted to simplify that original rational expression. Now I'm going to tell you a little something. Could we have used synthetic division? Yes. In this, with this division we could have. So let me write it over here. Synthetic division can be used when your divisor is of form x minus a. And that is the only time you can use synthetic division, when you have a divisor x minus a. So we have x minus 2. So let me remind you how to use synthetic division. Whatever your x minus 2, so x minus 2 is our divisor, and 2 goes in the box. So a is equal to 2. So a goes in the box, and we will write our coefficients placing zeros wherever we have a 0, wherever we have a missing power. So we have a 3, a negative 1, a negative 5, and a positive 1. Okay, let's go. Drop the 3. 3 times 2 is 6. Add them up. 5 times 2 is 10. Add them up. 5 times 2 again is 10. Add them up. And that is your remainder. So this is our remainder in synthetic division. Now, I want to tell you how to write the polynomial in front of that remainder. This represents a cubic. Remember, this 3 is raised to the third power. Well, think about anything raised to the third power divided by raised to the first power. Would leave a quadratic. So that is why this 3 here represents a quadratic. Okay? Excuse me, not that 3. That represented a cubic. This represents a quadratic. So as you can see, that 3, that 5, and that 5. So this is our squared term, our x term, and our constant term. Okay? Same result, but only can use synthetic when you're x minus a form. Okay, let's give this next problem a try. And we have a degree 4 polynomial in the numerator, a quartic, and we have a linear factor in the denominator. And let's go ahead and see what we have here. So we will go ahead and put 3x minus 5. And now we'll have 6x to the fourth minus 7x cubed plus x squared plus 2x. Okay? And so we're going to have 3x help me make my decision each time. Oops. And I want to go ahead and write a 0 here. And in long division, I use a 0 for any missing powers. It really helps when you drop all the terms down, okay? Okay, let's go. What would I multiply 3x by to get 6x to the fourth? So it'd be a 2x cubed. Once you make your decision, 2x cubed is multiplied by all of 3x minus 5. Let's give it a try. So that would be 6x to the fourth minus 10x cubed. We're going to subtract all of that, and we have 6x to the fourth minus 6x to the fourth. We planned it that way. Negative 7x cubed plus 10x cubed leaves a 3x cubed, and we're going to drop everything down. Okay, let's keep going. Focus on that 3x. What would I multiply 3x by to get 3x cubed? So that would be an x squared. Now we'll have 6x, 3x cubed minus 5x squared, subtract, and we end up with 3x cubed minus 3x cubed. And then we have x squared plus 5x squared, and that's a 6x squared, bringing the other terms down. Now we can still keep going. 3x multiplied by a 2x will give us 6x squared minus 10x. 6x squareds cancel. 2x plus 10x is 12x plus 0. And we can actually keep going. Multiply 3x by a positive 4, and we come up with 12x minus 20. And as you can see, that 0 helps us. 12x minus 12x. And be careful here because we have a 0 minus a minus, so that's a positive 20 as our remainder. Okay? So what would I write up here? Plus 20 over that divisor, 3x minus 5. Okay? Let's go ahead and integrate. So I'm going to rewrite this integral right here. And this is, probably have to go down a little bit more. This is equal, put a little star right here, equal to the integral of 2x cubed plus x squared plus 2x plus 4 plus 20 over 3x minus 5 dx. So that is equal to, add 1 and divide, so 2/4 or 1/2 x to the fourth plus 1/3 x cubed plus x squared plus 4x. And now we need to talk just a little bit about this integration. When we have the integral of 3x minus, when we have 3x minus 5 in the denominator here, let me highlight that. We are going to have to use u substitution. What I would do at this point is I would go somewhere else on my paper and I would just integrate 20 over 3x minus 5 dx. You could let u equal 3x minus 5. So du is 3 dx. And so 1/3 du is equal to dx. So this is actually, this integral is equal to 20 times the integral of 1 over u times 1/3 du. That's equal to 20 over 3 times the absolute natural log of the absolute value of u. And our u was 3x minus 5. Now, that may look a little bit difficult, but just maybe pause the video. All I did was integrate, you're not going to believe it, this last term. Actually, I can go ahead and highlight this, and you'll remind yourself of what we were doing. So this is equal to, or that is added 20/3 natural log absolute value of 3x minus 5 plus a constant. Okay, now you actually could use synthetic division if you factored out a 3 and then brought that back in later. Those terms back in later if you divided 3x minus 5 by 3. But I'll just leave that with long division there instead of attempting to get an x minus a form for the divisor. So I would just use long division there. Okay, let's go to our second and last. So now we'll try the technique of completing the square to help us rewrite the integrand. So in number 3, we can see that we have a rational expression and the derivative of the denominator is definitely not in the numerator. So it looks like we're going to have to do some other work. Division would not work either. So we're going to go ahead and complete the square. Before I do so, I think it might be worth noting that x squared plus bx plus half of b squared is equal to x plus half of b all squared. So we will be looking at this b coefficient, the coefficient of the x term, taking half of it and squaring it and adding that to both sides. And then we're going to use half of b to write it as a perfect square. I'll leave that there as we go ahead and work this one. Okay, so we're going to go ahead and just work with the denominator, and in a minute we will rewrite that integrand, okay, that integral. Okay, so let's go ahead and take a look at x squared plus 6x plus 10. And we're going to rewrite that as x squared plus 6x. And I'm going to put this in parentheses. I'm going to leave that plus 10 out here. So I'm going to take half of b, which is 3, and then I'm going to square it. So here we have, I'll write it in a different color, 6 over 2 all squared. Okay, so that's equal to 3 squared, or 9. So I'm going to add 9, and I'm going to subtract 9. Okay, that way I've not changed the problem. Okay, now we're going to rewrite this as x plus, and so half of b is 3, and that is equal to that. So if you need to convince yourself of that, go ahead and square x plus 3, and you'll see that that's what it's equal to. And then we have a plus 1. So let's see what that looks like. Let's go back into our integral, and we have 1 over x plus 3 all squared plus 1 dx. Now let's write that as a little more familiar. 1 over 1 plus x squared dx. What does that remind you of? All I did was move those terms, interchange those terms. Yep, you got it. That is a tan inverse. Now, you can go right into a tan inverse, and let me tell you why. If you let u be x plus 3, du is just equal to dx. So the derivative of this is just 1. So it can be your u without having to change anything else. We'll just go ahead and leave it like that. Okay? So now we have the integral of 1 over 1 plus u squared du, and that is the tan inverse of u plus a constant. Putting our u back in, it's an x plus 3. What I was mentioning here, since the derivative of u is just 1, you could actually just go from here to here, knowing it's the tan inverse of whatever was squared. Sometimes it's nice to write your substitution in. Well, that made it nice. Let's try a little bit more difficult one. Now, when you see a square root in the denominator and you're thinking about completing the square, it's not going to be a tan inverse. It's either going to be a sine inverse or a cosine inverse, okay? So if you remember what the derivative of the sine inverse of, I'll just use x, is equal to 1 over the square root of 1 minus x squared. Don't forget the derivative of the cosine inverse looks just like this, but the cosine inverse has a negative 1 in the numerator. So that's what we're headed for. This is possibly going to be a sine inverse or a cosine inverse. So let's go ahead and take this denominator, and we're going to work with it a little bit. Negative x squared plus 8x minus 15. I'm sure you remember whenever you complete the square, you definitely need to get that negative out of there. So negative 8x. I'm going to leave a little space. And now I'm going to put a minus 15. So that minus 15 is on the outside of the parentheses. So I still have an equality here, negative x squared plus 8x. Okay? Now remember, we're going to take half of b, which is a negative 4, and we're going to square it, which is a 16. So I'm going to add a 16 here. Now be careful, because when I add that 16, I'm really subtracting 16. So I need to add 16. I don't know if that makes sense, but you might want to convince yourself if you distributed this negative, you'd be adding really a negative 16. So you would have to add a positive 16. Okay? So let's keep going. Just trying to get rid of that arrow. Okay? So now we have the opposite, and don't forget, half of b is what actually becomes that perfect square. You can convince yourself of that, and that would be plus 1. So we're looking pretty good here. I'm going to rearrange it here so that when I go up to the integral, I'm set. So now let's go ahead and see what we have. This is equal to the integral of 1 over the square root of 1 minus x plus 4 all squared dx. Now, you can use u substitution, but once you see that the derivative of u is just 1, you can just write it without writing the substitution. You are really technically using integration by substitution. Let me see if you recognize this. This is equal to the sine inverse of x plus 4. Excuse me, that should be a minus. I wrote that wrong there, and that wrong there, and that wrong there. Okay. So, x minus 4 plus a constant. Okay? Think about taking the derivative of the sine inverse of something. It's 1 over the square root of 1 minus that something times the derivative of the something, which is just 1. So That's pretty neat. Okay, we're going to go to a very difficult problem. It's probably one of the hardest problems you'll come across, but it's worth working and talking about. Okay? So I'm going to go ahead and write that this is a difficult problem. And we learn a lot from these difficult problems. Okay, the derivative of the denominator is sitting in the numerator. It's not going to happen because we cannot come up with a 2x minus 4 in this numerator. So we know we can't jump right in. Also, it's definitely not a candidate for division. The numerator's degree is smaller than the degree of the denominator. So now we have to come up with another plan, and of course it is completing the square. Let's repeat our method. We're going to go over here and write x squared minus 4x. And I'm going to write a plus 20. Half of b is negative 2. And I'm going to square negative 2 and add 4. So if I added 4, I have to subtract 4. This is equal to x minus 2 all squared plus 16. Now it's a little confusing because we don't have a 1 over 1 plus x squared. That's really what our goal is. So let's see if we can figure this out. So we have a 32 over x minus 2 all squared plus 16 dx. So what we need to think about right now is that we need this 16 to be a 1. 1 over 1 plus x squared. So how are we going to do that? What could we possibly do? Well, we are going to multiply the numerator by 1/16 and this denominator by 1/16. Okay, so let's see what we've got now. Really, that's going to be that entire denominator. So the numerator is going to be 2. That's pretty nice. And then we have x minus 2 all squared over 16 plus 1 dx. So you might be thinking, whoa, I've got quite a mess, but let's just keep going. So we have 2 over, how about this? X minus 2 over 4 all squared plus 1 dx. Well, that's pretty nice because we have 1 over 1 plus x squared. Okay, so let's go ahead and get that 2 out of the way. Well, we could leave the 2 in and just see what this derivative is. Okay, so we're going to go ahead and let u be x minus 2 over 4. Of course, that's 1/4 x minus a half. So du is 1/4 dx, so 4 du is dx. Okay, so now we have the integral of 2 over u squared plus 1 multiplied by 4 du. Let's bring that 4 and that 2 on the outside. 1 over 1 plus u squared du, and we have a beautiful tan inverse. And we'll go ahead and plug our u back in, or substitute it back in. X minus 2 over 4 plus a constant. So although that was a difficult problem, I think we can always learn something from those. And that concludes this.